Hello and welcome to our 12th lesson in our study of functional analysis. So recall that in our previous video we talked about linear transformations, okay? So in this video we are going to talk about a particular theorem which is a special case of the Riesz representation theorem, okay? And I'm Guido Kandrino, a final year student of mathematics KNUST, and I'll be taking you through this lesson. So we will state the theorem and we will show it. Okay. So it says that let Kn to K be a linear functional, right? So the K there is a field. So it can be any field, raw numbers or complex numbers, or the set of rational numbers. Then there exists an x in Kn such that the linear transformation of x is given by the dot product of xy for all y in Kn. Okay, all right. So this is what the theorem states, and this question is going to let us show or prove the theorem. Okay, so the question says that what is the nature of the linear transformations from Kn to K? What is the nature of the linear transformations from Kn to K? Okay, so you could see that that was exactly the same thing the theorem states. Let Kn to K be a linear functional, and from the theorem it is the dot product of x and y, and let's show that here. So K is any field, right? So for the purpose of our proof, we can choose K to be R, the set of real numbers. Okay, so we have the linear transformation T such that this is our domain. So our domain is on Rn, and this is our range. Okay, so remember from our previous lesson that I told you that in finite dimensional space, right, when you have a finite dimensional space like we have here, the dimension, like our linear transformation, is always a matrix, and the dimension of it is given by 1 by n, right? So the dimension of the range by that of the domain. Okay, so that means that we know that this will be a matrix of dimension 1 by n, but what will be the nature? That's what you're interested in. All right, so we choose a certain vector x such that the vector s is in Rn. Okay, so if you could recall, when you're writing linear transformation, is given by Lx, but you see this Ls is in Rn, so that means that is a vector s1 s2 to Sn. Then this m here is the linear transformation, which is the matrix 1 by n. Okay, right. So but you should know that our m is 1 by n, right? So it means it has just one row, like it's a row matrix, right? Or we can say a vector here. So we have m is equal to y1, y2 to yn, right? So we just have one row in. So when we put this m here, when we put this m here, then we are going to have Lx will be equal to y1, y2, yn, then times x1, x2, xn. So you could see that when you multiply this, we are going to get y1 x1 plus y2 x2, and this is the same as x1 y1 plus x2 y2 to xn yn. And you could see that this is the same as the dot product of x and y, right, which is given by this. So it means that the nature of the transformation is going to be the dot product or the inner product. Okay, so we stated a special case of the Riesz representation, right? This was the theorem, and we have shown the reason why it is so. So that'll be all for this video, which was a short one. So we've already discussed equivalence norms, right? Our next video is going to be on equivalence norms, where we'll try to solve some important examinable questions under the equivalence norms. So thank you very much and see you in the next lesson.